Hello everybody. In this video, we are going to use a little bit of cleverness, a little bit of physics, and a little bit of observation and measurement to determine the energy output of the sun, the solar luminosity. And yes, we can do that with just a little bit of knowledge and just the right model that we can picture in our head that can guide us to how we can make a simple observation and use that to determine the entire energy output of the sun. This is a foundational thing because the energy output of the sun is equal to the energy being created by the nuclear fusion reactions in its core. So we are going to figure out some of the secrets of the sun. I hope you're ready for the journey. So what we're working towards is determining the solar luminosity. And I know it's been a couple of videos and a little bit of time and lots of new concepts. So let's remind ourselves what luminosity is. Luminosity is the total energy output every second of a object. So in this case, we're talking about a star, the sun. So the solar luminosity is the total energy output, how many joules per second. In other words, how many watts is the sun giving off? How much energy per second is the sun giving off? We could say, what is the luminosity of a light bulb in case that light right back there went out? Maybe I want to replace it with a 40-watt bulb, which tells me that it's giving off 40 joules per second. So how powerful of a light bulb is the sun? What luminosity, what wattage is the sun? That is our task. The total energy per second that the sun is emitting. And since we're talking about the sun, we're going to call that the solar luminosity. And this is a key part. This is the trick that we need to keep in mind because we're going to use the fact that we know that the sun is in hydrostatic equilibrium. It's not becoming larger or smaller. The gravity pulling things in equals the thermal pressure pulling out. So we have a nice stable star called the sun. Because those forces are balanced out, that means that the amount of energy coming out of the sun must be the same amount of energy that's being produced in the core by nuclear fusion. If it wasn't balanced that way, if the core is producing more energy, then the star would be puffing up, right? As it pushes that energy out into the sun. If the core is producing less energy, then gravity would be winning, the sun would contract down until those reached a balance of hydrostatic equilibrium. So when we determine the solar luminosity, we are actually determining how much energy is being produced by nuclear fusion in the core of the sun. That is profound. Let's figure out how we can do this. And what I want you to do is I want you to just picture the sun and the earth in your mind. And then I want you to do something that we can't really do. I want you to imagine that we have a switch where we can turn the sun on and off. So we could turn the sun off and it would be completely dark. We could turn the sun on and it would turn on. So what I'd like for you to do is imagine flicking the sun on for exactly 1 second and then turning it back off. If you flick the sun on for 1 second, that's going to send out a pulse of light that's going to be expanding its way out into space, right? Travels at the speed of light, and is getting further and further away. You can imagine that light distributed on the surface of a sphere as that light expands outward into space. Really, what we're looking at here is we are sending a pulse of 1 second. So all of the energy in that 1 second, that's going to be how much energy the sun is releasing in a second. And it's spreading out over the surface of the sphere. Energy per second over an area energy per second per square meter. This is a term that we're used to. It's a new one. That's our radiant flux. So this could even be tied to Stefan Boltzmann if you really want to start tying things in. We don't have to do that for this exercise though. Just imagine that we flick the sun on for 1 second and then turn it off. So we're going to see that pulse of light go out through the solar system. And we're going to imagine that pulse of light going out into the solar system until it reaches the surface, until it reaches the Earth here where we are. So we flick the sun on for 1 second and then we turn it off. It's sending out all the energy that the sun gives off in 1 second. So really this is going to, the entire amount of energy in this pulse is equal to the luminosity of the sun. That pulse goes out, it's expanding outward, until it reaches the Earth. So the pulse goes out, and as that sphere expands, that pulse, all the energy of the sun that the sun released in 1 second is getting spread out, is getting diluted over the entire surface of this giant imaginary sphere, this giant spherical pulse of light. When that pulse of light reaches the Earth, how much is reaching the Earth? Well, it's going to be diluted over the entire surface of the sphere. So if we want to talk about the radiant flux at Earth, it would be the luminosity of the sun divided by the surface area of that giant sphere that has a radius of 1 astronomical unit, the Earth to sun distance. And that would give me the energy per second per square meter that's reaching the Earth. Now, let's look at this a little bit differently. So that's going to give me, I can calculate the energy that's reaching the Earth per square meter per second. And that energy that's reaching the Earth per square meter per second, that radiant flux, is going to be equal to the energy output of the sun, the luminosity, how much energy it produces every second, divided by the surface area of this entire sphere with a radius of 1 astronomical unit, which is equal to 1.496 times 10 to the 11th meters. So notice if I could measure how much sunlight is reaching the Earth, how many watts per square meter reach the Earth, then I could calculate the luminosity of the sun. If I know how many watts per square meter reach the Earth, and I know that this pulse of light is spread out over the surface of a sphere, and the surface of the sphere has an area of 4 pi r squared. So then I can figure out I know the watts per square meter, I know the total number of square meters, I know the total watts. The question is, can we measure this flux at Earth? So by the time the light reaches the Earth, it's spread out over the sphere has a radius equivalent to 1 AU, and we can actually measure the radiant flux at Earth. And we can do this pretty routinely and pretty easily. It's best to use a satellite, get above the atmosphere, but we can measure that there are 100 or 1,361 watts per square meter that reach the Earth. It gets lessened as it goes through our atmosphere, but you can measure if you know how opaque the atmosphere is, then you can measure that here at the surface of the Earth. But that's the energy input from the sun at Earth. That's how much energy from the sun reaches the Earth at 1 AU away. It's 1,361 watts per square meter. We call this the solar constant. And if you're interested in things like climate change and the energy balance of the Earth and all of those sorts of things, this is a absolutely critical number. It's the amount of energy that we receive from sunlight per square meter here at Earth. Okay, so now we know we can just measure the solar constant. That's our radiant flux at Earth. That's this value right here. So we can just multiply that by the surface area of a sphere that has a radius of 1 astronomical unit, equal to about 150 million kilometers, 1.496 times 10 to the 11th meters. And that'll give me the total energy of that pulse that we sent out over 1 second. That'd give me the energy released by the sun every second. That would give me the solar luminosity. So let's just do that calculation. Nothing you ever have to do in this class, but just doing the algebra right here. The luminosity would equal the flux that we measure at Earth, our solar constant, 1,361 watts per square meter, times the total square meters of that imaginary sphere that has a radius equal to 1 AU. Could plug all that into the calculator, multiply all those numbers together. So 1,361 watts per square meter times this many square meters would give me 3.828 times 10 to the 26th watts. How bright of a light bulb is the sun? It is a 3.828 times 10 to the 26th watt light bulb. That is one really, really bright light. Enough. So here we are at 93 million miles away, and it brightens up our entire sky, keeps the Earth warm, and pretty much is the entire energy input for the planet Earth. Wow, stars are pretty powerful. But remember that this value right here, this 3.828 times 10 to the 26 watts, is the energy output of the sun. This is what we call the solar luminosity. So let's introduce one new solar unit, the solar luminosity. We're one solar luminosity, which we call luminosity. We just give it the letter L because we're creative. And it equals this value in SI units, 3 point, oh, sorry, that's typo, 828 times 10 to the 26. How much energy is this equal to? How much is the sun? How much energy is the sun producing every second? How can we conceptualize this crazy 3.828 times 10 to the 23rd watts? That's equal to 100, or that's equal to 10 billion 1 megaton nuclear bombs exploding every second. Megaton, 1 megaton nuclear bombs, 10 billion of them exploding every second. The sun is a star and is producing a ridiculous amount of energy. How? How? How can you produce that much energy? That is an absurdly large amount of energy. What possible physical process out there can produce this amount of energy? This baffled people for a long time. Is when they went through they did this calculation and they're like, this just doesn't make sense, because they did not yet know about nuclear fusion. So what kind of ideas were people playing around with? And they could realize that they were wrong. So one of the first ideas, what is the sun? You know, it's just a big fire in outer space. It's like a giant pile of wood or coal that is just cosmically burning. So this would be the sun's energy source is chemical energy, combustion. So we could use the mass of the sun and use knowing how much energy is produced by setting coal on fire by combustion. And you know what? The sun would burn with the current solar luminosity for about 50,000 years. So if you wanted it to power the solar luminosity by combustion, given the mass of the sun, you'd only have a solar lifetime of 50,000 years. We know, because we know the age of the solar system, we know when the sun became a star. That was 4.6 billion years ago. Clearly, the release of chemical energy that can power the solar luminosity for only 50,000 years, that can't be the answer. That's not even close to maintaining the solar luminosity for 4.6 billion years and another 5 billion years into the future. Okay, so uh, our good old friend Lord Kelvin, also called William Thomas, he came up with a different idea. He's like, okay, well, stars don't just pop into existence, they form. And people were playing around with the ideas of gravity. So maybe just the collapse and formation of the star, of taking a whole bunch of uh, material spread out over a huge volume of space and squeezing it down to the size of the sun. As you squeeze things together, squeeze the sun together, it's going to get really, really hot. It's going to convert all that gravitational energy into heat. Pretty clever idea, if you ask me. So you can do that calculation. You can figure out how much energy that gravitational collapse would create and then re-radiate it back out to space like a black body. And if you are re-radiating that out to space at the 3.828 times 10 to the 26 watts, you could power the solar luminosity for 20 million years. And this, at this time, Lord Kelvin was coming up with this idea just as geology was really starting to hit its major stride. And geology at this point had pushed the age of the Earth at least to 1 billion years old. So Lord Kelvin's like, damn, that doesn't work either. And it took until we understood the atom, until we had a concept of the atom and a concept of splitting and combining the atom, a full atomic theory that included fusion and fission, nuclear processes. That is how we charge, or that's how we power the sun. Must be something else. And we needed nuclear physics and atomic theory. And the nuclear fusion of hydrogen into helium can produce enough energy to keep the sun shining at this present luminosity, this ridiculous 3.828 times 10 to the 26 watts, and it can power the sun for 10 billion years. We know the sun is 4.6 billion years. This is how we know that the sun has another 5 billion years of life or so left. We know how much fuel is there, hydrogen is there. We know the process that's creating the energy, taking hydrogen and fusing those atomic nuclei together until you get helium. We know how much energy that produces. So we know the fuel source, we know how fast we're using the fuel source. We know that we can keep the solar luminosity going for another 5 billion years. All right. So I hope you really feel like you've started to find out some really cool secrets here. You're starting to see all this material come together, uh, and why we spent so much time building so much background knowledge. Because now we can tell really, really fundamental things like how much energy is being produced by the sun. And if we know that it's nuclear fusion, we can even figure out the lifetime of the sun. And we can start studying the fusion processes that are happening inside the sun, which is where we're headed next.